Oil plays a vital role in engine operation and lifespan. Engine oil's four primary functions include lubricating, suspending contaminants, dissipating heat, and acting as a hydraulic fluid for internal engine components. Lubrication represents oil's primary function. Inside the engine, moving parts generate friction. Oil reduces friction between these surfaces by creating a narrow film of oil molecules. This oil film reduces friction and heat. Oil also isolates and suspends harmful contaminants between oil changes. By suspending these particles, every oil change flushes this damaging material out of the engine. Oil also protects against rust and corrosion by coating all internal engine parts, preventing oxidation. As oil flows through the engine, it also removes heat from friction points isolated from the cooling system. Finally, vehicles use oil as a hydraulic fluid, engaging such components as VTEC rocker arms, VTC actuators, and the cam chain tensioner. In order to lubricate all the moving parts of the engine, all oil systems use common components. A typical system uses a pump to move pressurized oil throughout the engine, and then gravity returns oil back to the engine's sump to circulate through the engine again. In this section, we'll review these components. The lubrication system uses a positive displacement oil pump to pressurize engine oil passages. Some pumps mount at the front of the crankshaft, while other engines drive the pump using a chain connected to the crankshaft. The pump assembly includes a relief valve designed to limit total system pressure. The relief valve opens if oil pressure exceeds spring pressure due to extremely low temperatures or a blockage in the oil passages. When open, the relief valve directs oil back to the oil pan. From the oil pump assembly, oil flows to an oil filter. Inside, filtration media traps contaminants such as dirt or metal particles. If allowed to circulate in the oil system, these contaminants can cause wear on the bearing surfaces of the engine. Contaminants may be the product of combustion or an internal contaminant. Products of combustion include soot, carbon particulates, unburned fuel, and water. When oil remains in the engine too long, these contaminants overload the oil's ability to handle them and forms a coating called sludge. This sludge covers internal engine parts, blocks the return path to the oil pan, and reduces lubrication performance. Internal contaminants consist of metallic particles, spent oil additives, sulfuric acid, and nitric acid. These contaminants increase wear on moving parts, leading to greater friction, reduced oil pressure, and component failures. Some contaminants can plug the media inside the oil filter. When this occurs, the oil filter allows less oil to flow to the engine and reduces oil pressure. To prevent a blocked filter from starving the engine of oil, the oil filter includes a bypass valve. Should the filtration media block too much oil flow, the bypass valve opens, allowing unfiltered oil past the blockage. While the oil filter removes solid contaminants from the engine crankcase, the positive crankcase ventilation, or PCV system, removes gaseous contaminants. These contaminants include combustion gases that leak past the piston rings and water vapor formed through condensation. The PCV system draws in filtered air and uses engine vacuum to send crankcase vapors into the combustion chamber. This reduces sludge formation and helps increase engine oil life. Some engines use an engine oil cooler at the filter to transfer heat into the cooling system. One coolant line delivers coolant to the oil cooler, while a second line sends the coolant and heat into the engine water jacket. From the oil filter, engine oil travels through oil passages. Manufacturers machine each engine part so that oil passages match up from component to component. Because of this, always consider oil passages when positioning gaskets during engine assembly. In some cases, an oil passage includes an oil control orifice. This device reduces oil flow when installed in an oil passage. Whenever you disassemble an engine, keep track of these orifices. If you replace a block, be sure the new block has the correct oil control orifices, or transfer the orifices from the original block to the new engine before reassembly. Most oil passages end at a bearing. Bearings typically include a wear surface on the rotating component and a bearing surface. The bearing surface may be a machined surface on the component or a replaceable bearing shell. Between the two components, a tiny gap allows a narrow film of oil to isolate the parts. To deliver oil to this gap, bearings include a hole in their face. From this delivery point, oil fills the space between the shaft and bearing. From here, oil drains from the bearing edge and returns to the oil pan. As the oil flows from the friction surface, it removes heat and impurities. When assembling engines, make sure the oil hole in each bearing correctly matches the oil passage. If an oil passage on the bearing is in the wrong location, no oil flow occurs and the bearing will fail. A few oil passages end with oil jets, located on the block underneath the pistons. These oil jets spray oil into the cylinder to lubricate the cylinder walls and cool the piston bottom. The final system component is in the cylinder head, where oil passages feed oil to cam-control solenoids. When energized, these solenoids hydraulically operate VTEC pistons or a VTC actuator. Oil system faults include oil leaks and pressure problems. Oil leaks occur due to faulty mating surfaces, defective seals, and cracked or porous engine castings. Oil pressure problems include low pressure caused by wear, low pressure from low oil levels, or excessive pressure readings caused by oil system blockages. Problems in the oil system start with the basics. For instance, the correct oil fill level is critical for proper oil system function. Too much oil can interfere with crankshaft rotation. This can aerate the oil, leading to low oil pressure and possible engine damage. Excessive oil can also cause idle vibration, power loss, or even limit engine RPM. Finally, excessive engine oil may increase crankcase pressure, forcing oil out of the engine through seals or gaskets. Low oil level causes different symptoms. Hard braking or cornering can expose the oil pickup, drawing air into the oil pump and dropping system pressure. A low oil fill also reduces the system's ability to dissipate heat, increasing overall crankcase temperatures. For all of these reasons, always check the engine oil level before further troubleshooting. Oil leaks represent the most common oil system fault. Because oil does not evaporate and clings to vehicle components, the source of a leak can be very difficult to locate. To begin troubleshooting leaks, first perform a visual inspection. Look for oil trails at the bottom of the engine, up to the leak source. Keep in mind that most leaks do not occur without oil pressure. Because of this, starting the engine may create a steady drip from the leak. Leaks can also be checked using metal check spray. To use metal check, first clean and dry the area you want to test, and then spray metal check onto the test area. Any oil that contacts the test powder will turn a dark color, highlighting the source of the leak. Note, if the engine is not perfectly dry before testing, the metal check will identify the liquid cleaning solvents rather than an oil leak. If the engine was dry and no leaks appear after applying the powder, idle the engine or take the car on a test drive. This may force enough oil from the leak to activate the metal check. Once you've isolated a leak, determine the root cause of the problem before attempting repair. When the leak occurs at a flat gasket between two mating surfaces, make sure the sealing surfaces are flat and square before replacing the gasket. Also make sure the surfaces are clean during reassembly. Chunks of carbon or metal can hold sealing surfaces apart, causing leaks. Repair any problem you identify prior to reassembly. Also, check for loose or broken bolts near the point of failure. Loose bolts allow the gasket to relax, leading to oil leaks. If the leak occurs at a seal, make sure the seal is seated squarely in its bore, and inspect the rotating component for nicks or grooves. If the seal contact face has any damage, replace the rotating component. In rare cases, the engine may have a porous casting, which allows oil to seep through the engine walls. In some cases, these problems can be repaired using an epoxy patch. The best repair is to replace the component. As stated earlier, oil pressure faults may result in too much pressure or too little oil pressure. Low oil pressure can occur when air enters the suction side of the oil pump. Both low oil levels and internal leaks can cause this fault. To prevent suction side problems during engine assembly, make sure the pickup is properly sealed, mounted tightly, and the pump rotors have been primed with a thin coat of oil. These steps will provide a tight seal on the oil pump suction side, preventing oil starvation at startup. Finally, low oil pressure occurs when sludge builds up on the oil pickup screen, reducing oil flow to the pump. On some engines, you may be able to inspect the pickup screen by removing the drain plug, but the inspection typically requires oil pan removal. As we stated earlier, oil pressure also drops as internal engine components wear. Wear creates excessive clearance, reducing resistance and allowing oil pressure to bleed away. Our service manuals include engine inspection procedures for bearings and oil pumps. Low engine oil pressure can cause VTEC engagement problems or VTC position faults. If overall oil pressure drops, these faults may cause the PCM to set a DTC. The VTC or VTEC solenoid filter screen can also illuminate the mill. Sludge or other blockages can isolate the VTEC system even when overall system pressure is good. To confirm oil pressure faults, check actual pressure using a mechanical oil pressure gauge. Oil pressure should be at least 10 psi at idle and match the service manual specifications at 3,000 RPM. When owners complain of excessive oil consumption without any visible leaks, use the job aid designed to track oil consumption. The test begins immediately after an oil service and asks the customer to record the amount of oil consumed during the testing period at each fuel fill. The test should track oil consumption for twice estimated consumption mileage of the vehicle. Keep in mind that the test depends on the customer correctly measuring the oil they have added to the engine. To reduce test variations, consider asking the customer to bring the vehicle to the dealership for each oil check. The job aid also includes a flow chart to identify oil consumption faults following a logical step-by-step procedure. This procedure identifies oil consumption faults such as bad valve stem seals, bad piston rings, or scored cylinder walls. This concludes our coverage of the lubrication system. We hope this information helps you understand how the system functions and how to correctly troubleshoot and repair the oil system.